Hello. So we are heading into chapter 8 about estimation. So estimation is actually usually the ultimate goal of statistics. So we are learning statistics to estimate something unknown from the data, right? So then before talking about the actual techniques of estimation, I am going to give you a background. So it's like kind of a review of what we have done so far. First, let's understand what we are doing, how the data are generated. So we conceptually we distinguish the population and the sample. I have mentioned them several times before, and the idea is like let's think with an example. Like suppose that we would like to estimate the like how many votes candidate earns in the presidential election, for example. If if there is an election, then what percentage of voters are going to vote for a certain candidate? So that's what you want to know. And then, so in this estimation problem, the population is just everything you want to know. So if you know the population, that means you know the perfect information in that problem. Like in our example of election forecasting, the population is the voters. All the voters' political stance is known. Then you can exactly estimate the percentage of votes for each candidate. On the other hand, of course, by the way, the population is just everything you need. So if you know that, there is no statistics needed. Uh, you don't need any statistics, just it's a matter of computation, right? The statistics kicks in, like we need statistics because we cannot observe the whole population. Instead, we observe a sample, which is a smaller part of the population. For example, I wanted to know all the voters thinking, but that is not possible. Then what I can do is, like I could suppose I can interview 1,000 voters. Then that's your sample. So among, I don't know how many voters there are, but does not matter anyhow because we don't know. We are not going to observe them before the actual election happens. And then what we observe is the political surveys, political polls. And those observations are the sample. So in a simple diagram, population is just everything. And most of the population is not observed, but you only observe just a part of the sample. And then you can say that statistics is to make a guess about the population using the sample. So from this part, you'd like to guess how the original population looks like. So we have to understand to do that. We have to understand the relationship between the population and the sample. So we learned random sampling in the earlier chapter, and the random sampling is the process of choosing sample from the population. How the sample is generated from the population, right? So we learned it because we needed to go the other way. So random sampling is a process going in this direction from population to sample. But in practice, what we need to do is the other way. We observe the sample. From the sample, we'd like to make a guess about the population. That is statistical inference, right? So statistical inference is to make statements about the population based on the sample. Like, for example, like you did a political survey, and from the observations, you can say that a certain party or a certain candidate is going to get, say, 50% of votes, plus minus like with a marginal error of plus minus 3% point, something like that. You see these kind of statements in the news and the newspapers. That's exactly one example of statistical inference. And statistical inference is quite common in many places. And statistical inference methods are discussed in this chapter and two following chapters. Okay, so we need more things to set up. First, like we contrasted the population and the sample, we are going to contrast the parameter and the statistic. So now the term parameter is used in a slightly different way from the term parameters for binomial distribution or the normal distribution. Now the parameter is any numerical measure about the population, right? When we studied the binomial distribution or the normal distribution, the parameter meant something like if you know the parameters, then you know everything. It's a kind of a summary of everything without any loss of information, right? At that time, parameter meant that. But now it is like the same term, but used as opposed to the statistic. So the parameter is numerical measures about the population, and on the other hand, the statistic is the numerical measures calculated from the sample. So if it is from the population, that's the parameter. If it's from the sample, then that's the statistic. But so they are kind of they are opposing terms, but actually they can be the same thing. Like mean, you may calculate the average from the population or from the sample. So depending on where you calculate the mean from, it could be a parameter or a statistic. In the previous chapter, we learned the sample average has its own expectation. So sample, the average calculated from the sample is random, and it has a parameter, its own parameter of mean. So they are like you may think of mean as a parameter or as a statistic. Similarly, median, variance, probability could be calculated either from the population or from the sample. So depending on which information you use, it can be either parameter or a statistic. So just the form of the parameter or the statistic could be the same. However, like earlier, I contrasted the population and the sample this way. You can think about the population as an infinite number of observations, right? Anyhow, we are not going to observe the full set of the population. So we will assume that there are infinite observations. That's the population. And the parameter is the numerical measure calculated from those infinite number of observations. If they were possible, if they were available, that's how you would calculate the parameter. But on the other hand, statistic is more clear. You have a sample. A sample is just a number of observations, like Excel file. An Excel file contains the sample. So you can calculate whatever you want from the data, like mean, median, variance, probability, whatever. It is easy to calculate the statistics. You can easy to imagine how statistics is calculated, right? So then, so then another another thing, another way to contrast the parameter and the statistic is this way. So it follows from the previous explanation. A parameter is unknown, but we want to know. So this is why we need statistic. So as I said, a parameter is calculated from infinite number of observations. So of course, you never know that. You never observe infinite observations, so a parameter is unknown. But of course, we want to know. That's why we consider this. On the other hand, statistic is finite. From the finite sample, so based on a the finite observations, you can calculate the statistic. So you can calculate that, but the problem of the statistic is that it is random, which we discussed last time in the previous chapter. So a statistic is random, subject to random sampling error. So then, because of these properties, their roles are different. When you think of statistical inference, the target is a parameter. You are setting a parameter of interest. That's what you wanna guess, right? It's literally a target, and you are shooting at the target, and your arrow or your bullet is a statistic. You guess the value of the parameter with what you calculate from the sample. That's statistics. So now I think it's more clear. So on statistical inference is a kind of guessing, and then the correct answer, the unknown correct answer is the parameter, and your answer is, so when I ask you a question, your answer is statistic. You have to say something like guess something. Your guess is statistic. And in our notation with Greek letters, usually in general, just any generic parameter is denoted usually by theta. Theta could be a mean, a probability of variance, or collection of them. So usually theta is used to denote a parameter. On the other side, so we need to know, we'd like to know theta. What is the value of theta? And your guess is usually denoted as theta hat. So if you put hat on top of a Greek letter or on top of the parameter, that usually stands for an estimator for the parameter. You are estimating, you are guessing the parameter would be theta hat, right? It should be a number, right? So here, let me give you another example. So here, there are two major methods for statistical inference, two categories of inference methods. One is the estimation, which is easy to understand, and the other is a little bit weird method called hypothesis testing. So we are going to spend the following 2 chapters on hypothesis testing because it is not that intuitive. It's not like it has a very specific and strange structure to implement, to conduct the inference. So we are going to spend 2 chapters on this method. The major difference between these two are basically statistical inference is to guess about the parameter. But when you make a guess, in estimation, there is no hypothesis. There is no a prior hypothesis or assumptions or prejudice on the parameter. You have no idea where the parameter is. Just it's an open question like this. What percentage of voters support candidate A? Or what is the mean gas price of gas stations in New York City, right? So it's open question. I don't know. I don't know what would it like. What it would like. So there is just open question. On the other hand, hypothesis testing is based on literally a hypothesis. So you are testing after you impose a hypothesis. You already have a belief about assumption about the parameter. Like for example, I think I think more than 50% of voters are going to vote for candidate A. Is that right or not? It's yes or no question. I already made a statement without any evidence. Without any evidence. So now you prove it or disprove it. It's like yes or no question. Or I can say it like this. Is the mean gas price in New York City lower than $3 per gallon or not? I believe it's lower than $3 per gallon without any data, without observing any data. I just believe that. So yes or no? You tell me with data. That's hypothesis testing. So, of course, today we are going to study the process of estimation. Okay, here are examples. There are some examples. So, in presidential election prediction, in presidential election estimation, the population is all voters, and what you observe is survey respondents. And the parameter you'd like to know is the probability of voters supporting who would vote for candidate A. Here, it's all voters, so it's based on the population. But the statistic is the probability of respondents, survey respondents, who said would vote for candidate A. So the statistic is based on only on the survey respondents. That's the main difference. If you could observe all the voters, then you know everything. So you know the parameter, so you don't need any inference. You don't need any statistical inference. But because we could not observe all voters, then what you can do is take sample and calculate some statistic which can be used to guess the parameter. Similarly, gas price in New York City. The population is all gas stations in New York City. If you could visit every single gas station in New York City, then the answer is clear. You can get the answer, right? You can get the mean gas price in New York City. But assuming that you cannot visit all gas stations, then you need to randomly choose a few gas stations and check their prices. Then parameter we'd like to know is the mean gas price if you could visit all gas stations. But that's not possible, that is unknown. So the statistic you use to estimate the parameter is the mean calculated from what you observed. Right? So these are simple examples to set up the ideas and the terminology. So here, let me ask you one last question about this structure. So suppose that now we are changing the example. What you are going to do here is, I used this example before. Suppose that you are inspecting batteries. So you are in charge of inspecting the battery shipments into your factory, and you'd like to estimate the defect rate. That is the parameter, right? I already said it. So you wonder how many batteries shipped to your factory are defective. Then it is a statistical inference because you cannot check all the batteries. You cannot inspect all the batteries. Then, if you can imagine the situation, think about what corresponds to what. Okay, so actually I already told you the answers. So the population is all the batteries shipped to your factory. If you could inspect every single battery you received, then you can calculate the parameter, which is the probability of defective batteries among all the shipped batteries. But it is impossible to inspect every single battery from in the shipment. So usually a few randomly chosen batteries are inspected and only checked how many of them are defective. So the sample you observe is randomly chosen inspected batteries, and in that case the statistic will be the probability of defective batteries among those inspected. So the correct answer is E. Like actually all of these four statements are correct, right? So I want you to understand the basic framework, basic structure, underlying structure for statistical inference. What we observe and what we don't observe, but what we want to know. So population and sample. So distinguishing them is important in understanding the the rationale behind this statistical inference. Okay, in the following video, I will keep talking about parameters and statistics. Okay, see you there. Bye.